In this lecture, we will discuss about spherically symmetric potentials and hydrogenic atoms. In the previous lecture, we have already discussed about angular momentum or orbital angular momentum in quantum mechanics. So, before listening this lecture, I request you to study those lectures very carefully, because the results that we have derived in case of orbital angular momentum will be used in deriving the Schrodinger equation for hydrogen atom. So, let us start our discussion. Now, in this lecture, we are going to study about symmetric potential or spherically symmetric potential. So, what do you mean by spherically symmetric potential? Suppose Vr is a potential. We are going to study the motion of a particle where Vr is a potential and it depends only on the magnitude r of the position vector r. Position vector is r and Vr depends only on the magnitude r of the position vector r. This r is vector quantity of the particle with respect to some origin. So, Vr depends only on the magnitude r of the position vector. Such a potential is called a spherically symmetric potential or a central potential. So, now we study separation of the wave equation into radial and angular parts. If m is the mass of the particle, then its Hamiltonian is capital H is equal to minus h cut square by 2m del square plus Vr. We already know about Hamiltonian operator. Now, we are concerned when Vr is spherically symmetric. Here the potential Vr that is spherically symmetric, that we have already discussed. It is very convenient to use the spherical polar coordinates. The spherical polar coordinates for del square operator. So, we have already discussed about the form of the del square in spherical polar coordinates. We have already learned in our earlier lectures. So, at first what we have to do? We have to express del square in spherical polar coordinates, and you can also see some standard mathematical physics textbook for expressing del or del square operator in spherical polar coordinate. So, after expressing del square in spherical polar coordinate, this is the term which is contained in the third bracket, that is the spherical polar coordinate representation for the operator del square. So, this is minus h cut square by 2m, and this term in the third bracket is del square plus Vr. Now, in the earlier lecture where we have discussed about orbital angular momentum, there we have learned that square of the orbital angular momentum, that is L square, that can be represented as minus h cut square 1 by sin theta del del theta sin theta del del theta plus 1 by sin square theta del square by del phi square. We have learned this expression in earlier lecture, that is a lecture about orbital angular momentum. So, if we use this result and if we use the value of L square in this equation, that is in equation for H, so we can see that capital H that can be represented in terms of L square. You see, that is second and third term that has been expressed in terms of L square. So, H, that is Hamiltonian, now becomes minus h cut square by 2m 1 by r square del r square del r minus L square by h cut square small r square plus Vr. The time independent Schrodinger equation for the particle can be written as h psi is equal to E psi. We know that is the time independent Schrodinger equation. So using this Hamiltonian operator, let us write the time independent Schrodinger equation, but it is in spherical polar coordinate. So h into psi, this is the value of h psi is equal to E psi, but you see that the wave function psi has been represented in terms of spherical polar coordinates, that means r, theta and phi. Now this equation has been slightly rearranged. The angular momentum term that has been put in the right hand side. Now this equation can be solved by using the method of separation of variable. So to use the separation of variable, we have to write psi in terms of multiplication of two functions. One function is the coordinate of small r only, that is we are writing psi is equal to capital R, which is a function of small r, and capital Y, which is a function of theta and phi. Now it should be noted that we have already learned about capital Y function in earlier chapter about orbital angular momentum. Now if we set psi is equal to capital R into Y and substitute the value of psi in the previous equation, that means in this equation, then after a little bit of rearrangement we can write in this way. So we are having this equation. If we substitute the value of psi, psi has been expressed in terms of capital R and capital Y. So after the substitution of the value of psi in the equation 12.6, we are having this equation. Again we have to simplify this equation. How to simplify? We will divide this equation by capital R into capital Y divided by small r square. So after division by this expression, we will have this equation. This is this equation 12.7, and if you look carefully, and the left hand side of this equation depends only on small r. You see this left hand side depends only on small r, and the right hand side of this equation depends on theta and phi. Therefore both sides must be equal to a constant, and we are calling this constant as lambda. So we obtain the radial equation, that is left hand side that after equating to lambda and putting all the term in the right hand side, we are obtaining this radial equation 12.8. You see that equation 12.8 contains the function small r only, and after equating the right hand side with lambda and after a little bit of rearrangement, we can write L square into Y, L square into capital Y, that is equal to lambda into h cut square into capital Y. Equation 12.9, you see very carefully equation 12.9. So this equation is known as the angular equation because it contains the function theta and phi. Y depends on theta and phi. So this equation is known as the angular equation, and this equation, as it contains the function small r, that is why this equation is known as the radial equation. So we have separated the Schrodinger equation into two parts. One is the radial equation, this one is the radial equation, and another one is the angular equation. Now let us focus on the angular equation. This is the angular equation, L square Y is equal to lambda into h cut square Y. Now we can recall that in our earlier lecture we have already discussed about such type of angular equation, and this equation is actually an eigenvalue equation for the operator L square. Why we are saying eigenvalue equation? Because you see L square into Y, that is equal to lambda h cut square into Y. So lambda h cut square is the eigenvalue of L square, Y is the eigen function. So this is known as the eigenvalue equation for the operator L square. And we have already learned in earlier chapter about orbital angular momentum that such type of equation gives the physically acceptable solution only when lambda is equal to small l into L plus 1, where the value of L is 0, 1, 2, etc. Thus, the eigenvalues of L square are L into L plus 1 into h cut square, where L equal to 0, 1, 2. The corresponding eigenfunction y is the eigenfunction. In this equation, y is known as the eigenfunction, and the eigenfunctions are represented in terms of the spherical harmonics y lm theta phi. We have also learned this y lm theta phi is the eigenfunction, and the spherical harmonics y lm theta phi are also eigenfunctions of the z component of the angular momentum Lz. We have already learned that ylm is the simultaneous eigenfunction of L square and Lz. So, Lz into y, that is equal to ml into h cut into y, where ml is equal to minus L plus 1 in this way up to L minus 1 and L. So, this is ml. And it may be noted that so long as the potential is spherically symmetric, whatever be its precise form, the angular eigenfunctions are always the spherical harmonics. This we have to note carefully. Now, let us focus on the radial equation. So, the radial equation, if we substitute 12.10 into 12.8, 12.10 means this equation. If we put the value of lambda is equal to L into L plus 1, where in this equation, that means in this radial equation, this one is the radial equation, we have already told about that. Just we are putting the value of lambda here. So, after putting the value of lambda, the radial equation becomes like this. So, this is the radial equation. Now, we have to simplify this equation. How to simplify? We are assuming that capital R, which is a function of small r, that is equal to u divided by small r. Then the equation for the new radial function u becomes like this. So, what we are doing? We are just converting capital R in terms of a new function u. Capital R is equal to u by r. So, after this substitution, this equation becomes like this: d square u by dr square plus 2m by h cut square e minus v minus L into L plus 1 h cut square divided by 2m r square into u r is equal to 0. Now, this equation shows that the radial motion is similar to the one-dimensional motion of a particle in the effective potential. Effective potential means, actually in the Schrodinger equation, this should be E minus V. So, this whole term containing the second and third term, we are considering this as a single term, V effective. We are writing V effective as Vr plus L into L plus 1 into h cut square by 2m r square. So, this term is known as the V effective. Now, in this effective potential, there is an additional term L into L plus 1 h cut square by 2m r square. So, what is the significance of this term? That is, apart from the term here, there is an additional term here. So, what is the significance of this term? This term is due to the centrifugal barrier, which is a consequence of the non-zero angular momentum of the particle. So, how we can understand this? Because you see that according to classical mechanics, if a particle has angular momentum capital L about an axis, then its angular velocity is omega is equal to capital L by m r square. We have learned this relation in classical mechanics, because capital L, that is angular momentum, that can be written as m omega r square. So, omega, that is equal to L by m r square. What is omega? Omega is the angular velocity, capital L is the angular momentum, m is the mass, and r is the distance of the particle from the axis. And we also know that the expression for the centrifugal force is m r omega square. Now, what is m r omega square? If we put the value of omega from here, then the centrifugal force becomes L square by m r cube. This is the value of the force. Now, if this is the value of force, then what will be the value of potential? You know the relation F is equal to minus dV by dr. So, from that relation, potential can be found from the expression of the force. This is the expression of the force. So, the corresponding potential from the relation F is equal to minus dV by dr is L square by 2m r square. This is the expression for the potential. Now, if you write in place of L square, that is equal to L into L plus 1 into h cut square. We have already discussed about that. That is L square is equal to L into L plus 1 into h cut square. So if you put the value of L square in this expression, you see that this term is exactly same as this term. So what we have established till now, that is from the definition of the centrifugal barrier, we have established that this potential comes from the centrifugal force, or this term can be known as centrifugal potential barrier, this second term. Now this term tends to infinity as r tends to 0. From the expression we can tell, because as r is in the denominator, so as r tends to 0, this term will become infinite. Thus it acts as a repulsive core and prevents the system from collapsing, because if you make the particle very close to the axis, then what will happen, this term, this potential term will become repulsive one, and it will prevent the system from collapsing, because if the particle merge with the axis, then what will happen, the system will collapse. So this term will prevent the system to collapse. And if we plot the equation, that is centrifugal barrier, this term, that is L into L plus 1 by h cut square by 2m r square, this axis is the potential axis, and this is the distance of the particle from the axis, this is smaller. So this is potential axis, this is smaller axis. So this curve is a centrifugal barrier, and the below, that is VR curve, that is a normal potential. It generally become it is negative, and it becomes 0 at infinite. So VR is like this. So if we write VR plus L into L plus 1 h cut square by 2m r square, that is V effective. So V effective is the resultant of these two curve, that is this is the first curve, this is the second curve, and the middle curve, that is V effective, that is the resultant of the two expression. So this one is the curve of the V effective. Now in order to proceed further with the solution of the radial equation, we must know the precise form of the potential VR. So we have already established the form of the radial equation. This is the form of the radial equation. So if we want to solve the radial equation, then we have to know the exact form of the potential VR. If we know the exact expression of the potential VR, then we can easily solve this radial equation. Now in what follows, we shall solve the radial equation for a hydrogenic atom. So our aim is to solve the radial equation for a hydrogenic atom. So what is hydrogenic atom? It consists of a nucleus, there will be a nucleus and an electron interacting via the attractive Coulomb force, which depends on the magnitude of the distance between the two. So there will be a nucleus, and an electron will encircle the nucleus, and there will be some attraction, that is attractive Coulomb force, and Coulomb force depends on the distance between the electron and the nucleus. And now what we will study? We will study a two-body system. Why two-body? Because you see there is an electron and a nucleus. So at first we will learn that is what is a two-body system, and if the potential energy depends only on the coordinates of the one particle relative to the other, then the problem can be reduced to an equivalent one body problem along with a uniform translational motion of the center of mass of the two body system. So basically the meaning of this sentence is that we can reduce a two body problem into one body problem by employing the concept of the center of mass of the two body system. So now we will learn that is how a two body system. What are two body systems? Where there is a nucleus and an electron. Such a systems, basically the hydrogenic atoms, are two body system. So two body systems can be reduced to one body system, and in that case the radial equation can be solved very easily. So let us learn how to reduce two body system into one body system. So we are considering two particles of masses m1 and m2, and there is an potential. Why there is a potential? Because these two particles interacts with each other. So from the interaction there is a potential. So that potential V is a function of R1 minus R2. Why R1 minus R2? R1 minus R2 is the relative coordinate of the particles. If the position vector of m1 is r1 and the position vector of m2 is r2, then the relative distance between the m1 and m2 will be r1 minus r2, and the potential V depends on this relative coordinate r1 minus r2. In that case, the time independent Schrodinger equation for the system can be written in this fashion, that is minus h cut square by 2 m1 del r1 square. This term is for the m1 particle. Similarly, minus h cut square by 2 m2 del r2 square, that is for the second particle, plus we are writing V r1 minus r2 as potential V depends on the relative coordinate, and we are writing psi r1 comma 2. Why we are writing psi r1 comma r2? Because the position vector of m1 is r1 and the position vector of m2 is r2. That is why psi is a function of r1 comma r2. So that is equal to E into psi. So this is the time independent Schrodinger equation for the two body system. Now E is the total energy of the system. In the right hand side we have written capital E. Capital E represents the total energy of the system. Now what is actually the relative coordinate? We have already told that r1 is the position vector of m1, r2 is the position vector of m2, and we can write small r, that is equal to r1 minus r2, that is the relative coordinate for the system. And we will introduce another coordinate, that is capital R. What is capital R? Capital R is known as the center of mass coordinate. So capital R can be written in this way, that is m1 r1 plus m2 r2 divided by m1 plus m2. We have already learned in our mechanics, that is center of mass coordinate can be written in this way. Now what we will do, we will proceed in a very simple method, and after some algebraic calculation we can show you. See very carefully the left hand side. The left hand side is minus h cut square by 2 m1 del r1 square minus h cut square by 2 m2 del r2 square. So this expression can be written in this way, that is minus h cut square by 2m del capital R square minus h cut square by 2 mu del small r square. So this calculation is very simple, but you have to do some steps in this particular derivation. We have skipped those steps, but you can very easily prove this equation. Just we have to use this equation, that is the relation between small r and r1 r2 is this. This is the relative coordinate, small r is equal to r1 minus r2, and the relation between capital R and r1 r2 is this one, m1 r1 plus m2 r2 by m1 plus m2. So this is the relation between small r, capital R and r1 r2. From those relations only we can show that this left hand side can be equal to this right hand side. You see, in the right hand side we are not writing r1 or r2, that is individual coordinates of m1 and m2. We have expressed the right hand side in terms of a center of mass coordinate capital R and the relative coordinate small r, where capital M is equal to m1 plus m2, and here there is a term mu. Mu is equal to m1 m2 divided by m1 plus m2. What is mu? Mu is known as the reduced mass of the two particle system. Now the Schrodinger equation, this Schrodinger equation of the two body system, as we have transferred the first two terms like this, that is in equation 12.18. So after substitution of this term, the Schrodinger equation for the two body system can be simplified by equation 12.21. This equation, that is minus h cut square by 2 capital M del r square minus h cut square by 2 mu del small r square plus Vr into psi is equal to E into psi. Here we have to note very carefully, that is, now the wave function psi is a function of two coordinates. One is the capital R, that is the center of mass coordinate, and another one is the small r, that is the relative coordinate. Now the potential V, you see the potential V depends only on the relative coordinate. The wave function psi capital R comma small r can be written as a product of the functions capital R and small r, as it depends on capital R and small r. So we can write psi as a product of phi, as a phi is a function of capital R only and psi is a function of small r only. So psi can be written in this product format. Now if we substitute the expression of psi in this equation, then what we can do, we can separate this equation into two parts. The first part is like this: minus h cut square by 2 capital M del capital R square phi is equal to E r into phi r. We are writing E as by giving suffix capital R, because this equation depends only on the center of mass coordinate. That is why we are writing energy term for only the center of mass. And another equation will be minus h cut square by 2 mu del small r square plus Vr into psi r is equal to Er into psi r. Here you see in the energy expression we have given a suffix small r, because you see this equation depends only on the small r. So basically what we have done, we have used again the separation of variable method, and by the application of separation of variable method we have separated the equation 12.21 into two new equations. One equation involves only the center of mass coordinate and another equation involves only the relative coordinate. So this equation concerns the motion of the center of mass, because you see the coordinate is the center of mass coordinate. So this equation deals with the motion of the center of mass. It says that the center of mass moves as a free particle of mass capital M and energy Er. The center of mass, it moves as if a free particle, because you see there is no potential terms here. In this equation there is no potential term. So we can say that center of mass moves as a free particle of mass capital M and energy Er. And this equation describes the relative motion of the particles, because see here small r is involved. That is why this equation describes the relative motion of the particles. It says that the relative motion is same as that of a particle of mass mu moving in the potential Vr. So we can consider that a single particle of mass mu moves in a potential Vr. This is a simply Schrodinger equation, and this equation describes the relative motion of the particle. But we can say that this is the motion, similar motion of a particle of mass mu. We are not saying that there are two masses. We are saying that there is only one mass. The reduced mass is mu and the particle is moving in a potential Vr, and the total energy E, that will be Er, E capital R plus E small r. In a physical problem, we are mainly interested in the eigenvalues and eigenvectors connected with the relative motion. So relative motion is more important. Therefore, we shall be concerned only with the solution of equation, this equation 12.24. Thus, by separating the center of mass motion, here we have already separated the motion of the center of mass, and therefore the solution of the problem gets considerably simplified. Now in the next lecture we will describe the motion of the hydrogenic atom. So far in this lecture what we have discussed the method of separation of variable. We have discussed how a two body problems can be reduced in a one body problem, and later we have learned that is how after separating the motion of the center of mass, the two body problem can be reduced to a one body problem when we are expressing the masses of the two body in terms of a reduced mass mu, and in this way the solving of the Schrodinger equation for a two body system becomes considerably simplified. So I think you have already understood this lecture, and thank you all for listening this lecture.